Today we're going to discuss about finite dimensional norm space. Okay. Now we also discuss one lemma about linear combination. Okay. This lemma of linear combinations. This lemma, first right statement of this lemma, let x1, x2, xn be a linearly independent set of vectors. Be a linearly independent set of vectors. Okay, in a normed space X, in a normed space X of any dimension, then there is a number c greater than 0. Then there is a number c greater than 0 such that for every choice of scalar, such that for every choice of scalar alpha 1 alpha 2 alpha n, we have norm of alpha 1 x1 alpha 2 x2 alpha n xn greater than equal to c norm of alpha 1 norm of alpha 2 norm of alpha n, where c greater than 0. How we proved this lemma? This one is an important lemma. Just x1 are linearly independent set of vectors of any dimension. Then there is a constant c greater than 0, and also these linear combinations of x1 x2 xn for alpha are arbitrary constants greater than equal to some constant that is not positive constant multiplied by this coefficients modulus. Okay, this greater than 0. How we prove this one? Now we start proof of this lemma. This one is an important lemma, so we prove it now. Let is equal to norm of alpha 1 norm of alpha 2 norm of alpha. Okay, then if s equal to 0, then all alpha j are 0. This implies that, so that one holds for any c, so that this one marked as 1, so that one holds for any c. Okay, now we're going to let s greater than 0, then 1 is equivalent to the inequality which is obtained from 1 by dividing s. So we write dividing s, then this one is beta 1 x1 beta 2 x2 and beta n xn. Norm of these greater than equal to c, for beta j equal to alpha j by s. Okay, and obviously summation j equal to 1 to n beta j equal to 1. Okay, now it suffices to prove that, hence it suffices to prove this one we marked as 2, hence it suffices to prove that The existence of a c greater than 0. The existence of a c greater than 0 such that 2 holds for every n tuple of scalar. Such that 2 holds for every n tuple of scalar. N tuple of scalar beta 1 beta 2 beta n, beta 1 beta 2 dot beta n, where summation beta j modulus equal to 1. Okay, now we're going to this. Suppose that this is false, that means suppose this one false, this 2 is not whole, is false, then there exists a sequence ym, then there exists a sequence ym, okay, of vectors, sequence of vectors. There exists a sequence of vectors ym, where ym equal to, beta 1 m x1, beta 2 m x2 dot beta n m xn, where summation of beta j m equal to 1, j equal to 1 to n, such that norm of ym tends to 0 as m tends to infinity. We reach all portion above portion. Such that norm of ym tends to 0 as m tends to infinity. Okay, now since summation beta j whole to the power m equal to 1, we have modulus of beta j m less than equal to 1. Hence for each fixed j the sequence, hence for each fixed j the sequence beta j m equal to beta 1 1 beta 2 1 dot is bounded. Consequently, by Boolean-Oester's theorem, beta 1 m has a convergent subsequence. Okay, now let beta 1 denote the limit of this subsequence. Let beta 1 denote the limit of the subsequence. Limit of this subsequence, and let y1m denote the corresponding subsequence of ym, and let y1m denote the corresponding subsequence of y part m ym, then by same argument y1m has a subsequence y2m. y1m has subsequence y2m has a subsequence y2m for which the corresponding subsequence of scalar converges, for which the corresponding subsequence of scalars beta z, corresponding subsequence of scalar beta 2m converges. Okay, let beta 2 be the let beta 2 denote the limit and continuing in this way after n step we obtain a sequence. After n steps we obtain a sequence. We obtain a subsequence ynm where summation j equal to 1 to n gamma j m and xj, where summation j equal to 1 to n gamma j m equal to 1 with scalars gamma j m satisfying gamma j m tends to beta j as m tends to infinity. Okay, now hence as n tends to infinity, now here is our portions. Hence as n tends to infinity, ynm equal to summation of j equal to 1 to n gamma j m xj tends to y equal to j equal to 1 to n beta j xj, where summation of beta I equal to 1, so that not all beta j can be 0, so that not all beta j can be 0. On other hand, ynm tends to y implies that norm of ynm tends to norm y. Okay, by continuity of norm, and since norm of ym tends to 0, by assumption by assumption, and ynm is a subsequence of ym. Ynm is a subsequence of ym. We must have ynm. We must have ynm tends to 0. Okay, norm of ynm tends to 0. Hence, norm of y equal to 0. Hence, norm of y equal to 0. So that this implies that y equal to 0. This contradicts y not equal to 0. This contradicts y not equal to 0. So the lemma is proved. Okay. Then we also show that this alpha 1 x1 dot alpha n xn greater than equal to c multiplied by norm of alpha 1, norm of alpha 2, norm of alpha n. Okay, so we going to another another problem. This one is an important theorem also. In a finite dimensional norm space, all norms are equivalent. By using this lemma, we also prove this one. Okay. We write this statement of the theorem. In a finite dimensional norm space, all the norms are equivalent. All the norms are equivalent. Then we now prove this one. Or more generally, we prove any norm this one is equivalent to any other norm. Okay, this one. Now let dimension of x equal to n prove. Let dimension of x equal to n and e1 e2 en be any basis, and e1 e2 dot en be any basis for x. Then every x belongs to x. Then every x belongs to x has a unique representation. X equal to a1 e1 a2 e2 dot an en. And then by this lemma, then by above lemma, we get norm of x greater than equal to c multiplied by norm of a1, norm of a2 norm of a, for c greater than 0. Okay. Now on other hand, the triangle inequality gives On other hand, the triangle inequality gives norm x0 less than equal to summation j equal to 1 to n norm of alpha j norm of xj or ej here. Okay, 0 less than equal to k summation of j equal to 1 to n alpha j, where k equal to maximum of norm of ej 0. Now we proceed this one. Then we prove that a norm of x0 less than equal to norm of x, where a equal to c by k. Okay, here not aj, we construct aj, not write alpha j. Okay, then a equal to this one. And now other inequality in 3 is now obtained by interchanging the rule of this one. Okay, other inequality obtained by the change of role of this one. Okay, so we get these two norms are equivalent. Okay, so we get these two norms are equivalent. So we get norm of x0 and norm of x are equivalent. Okay, now we're going to prove of one example of this problem. We now proceed with one example. This example is that x be a normed linear space. Okay, then norm of x1 equal to summation mod of x1 mod of x dot 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 mod of xn, and norm of x2 equal to summation of I equal to 1 to n norm of xi square whole to the power half, and norm of x infinity equal to maximum of xi such that 1 less than equal to I less than equal to n. Then norm of x1 equal to this one mod of x1 mod of x2 dot 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 mod of xn less than equal to n into maximum of xi 1 less than equal to I less than equal to n equal to n norm x infinity. And obviously norm x infinity less than equal to norm x1 less than equal to n norm x infinity. Then norm x infinity 1 and norm x infinity are equivalent in a finite dimensional norm space. Okay. Next we're going to one theorem. These theorem are too easy. Now we proceed one definition, then one theorem. Okay. This theorem is too easy, but first we write one definition. Let x and y be normed space. Let x, y be normed spaces. Okay. Then x Cartesian product y is a normed space under the norm. Is a normed space under the norm. Norm of x y. X Cartesian product y equal to norm of x plus norm of y. For all x y belongs to x Cartesian product y. Okay. Now we also write this one. Let t x to y. Let t x to y be a linear operator. Be a linear operator. Define norm t x to r plus y. Define norm t. Okay. This one norm t x to r plus by norm xt equal to norm xx plus norm of txy. Okay, txy be a linear operator, then this one is false. Okay, then clearly t is a norm for all x belongs to x. Then clearly t be a norm, which is called the graph norm of x, which is called the graph norm of x induced by t. Induced by t. Now we're going to write this two definition, the graph norm of x induced by t, and also we write x Cartesian product y is a norm space under this norm. Okay, now we proceed one theorem. This theorem be let x y be normed spaces. Let x y be normed linear spaces, and t x to y be a linear operator. Let t x to y be a linear operator. If dimension of x less than in plus infinity, then t is bounded. Let x be finite dimension. Let x be finite dimension, then let x be finite dimension. Then norm of txy less than equal to norm of x plus norm of txy. Okay, and the norms are equivalent then norm t and norm x, and norm t and norm x are equivalent. Okay, then then there exists m and m greater than 0 such that m norm x x less than equal to norm x t less than equal to capital M norm x x. Okay, we write the definition of norm x t. Then this implies that thus norm of t x y less than equal to capital M norm of x. Okay, for all x belongs to x. Hence, hence this implies that norm of t less than equal to m. Thus, t is bounded. Okay, so today we discuss more problems and also understand all the problems. So today we stop here.